This is lecture 18 for continuing our discussion on the continuity equation. So let's go to the bias lamping. So I just discussed how can we implement the bias lamping. So simply speaking, the only difference between the equilibrium case and non-equilibrium case was just the boundary condition for our electrostatic potential. For example, at equilibrium, we have the equilibrium potential determined by only dopant density. So that was it. And if we have a certain applied voltage, then simply speaking, we just add this additional voltage to our electrostatic potential. That is enough to consider the non-equilibrium cases. So then natural question is, how about electron density and hole density? Oh, don't worry, even in the case of non-equilibrium case, still we assume that at boundary we have equilibrium electron density and equilibrium hole density. Once again, these quantities are just given from our dopant density. So now let's have a look at the result of the simulation. So this is current conduction, and for the IV characteristics means that we just apply positive voltage to our anode, and starting from this equilibrium condition where the applied bias is equal to 0, then we just move to positive anode voltages. For example, in this example, in order to arrive 0.2 volt, we just introduce 1, 2, 3, 4 steps. It means that we just took 0.05 volt as a bias step. So starting from this equilibrium solution, we first try to solve the condition where the anode voltage is just 50 millivolt. Yes, after it successfully done, then we move to the next bias point, and next bias point. I know that you have already done such kind of a bias lamping for your previous homework MOS system. However, at the time, the equation of your interest was non-linear Poisson equation. So, although when you apply 1 volt or 0.5 volt, in every case there is no current conduction through this MOS system. However, now when you consider this PN junction, when you apply non-zero bias voltage to the anode, then you have non-zero value of current conduction. So in this linear scale, so please note that this is just written drawn in the linear scale up to, for example, here or there, it is difficult to find out any meaningful value of our terminal current. However, when you go to this bias condition or beyond, then you can immediately understand the current is no longer negligible and quite much conductive behavior is observed. So this is the typical linear scale. So this character, the current is written in linear scale, and also voltage is drawn in linear scale. However, Another one also frequently used is like this. Take the log 10 of our current and still we have linear voltage. In this case, although we have the same data, however, now you can understand below 0.8 in this linear scale, all of them were just considered as quite close to zero, but you can now understand even in these cases there are highly much differences in this range. So comparing the values and 0.2 volt and 0.8 volt, there is really huge difference. How large is it? It is more than 10 orders of magnitude difference is observed in this case. So please note that when you draw your IV characteristics, in many cases you just draw two things with the same data points, linear scale and semi-logarithmic scale. So now you can see that this kind of simulation capability can be achieved without almost spending additional implementation of effort. So once you just change the bias lamping or the boundary condition for your potential, then you will get the solution, converged solution. After that, you can calculate anode current or cathode current. So do you remember how we did it? So if you have, let's say that this is your cathode current and this is your anode current, then this is the end point and this is the nearest neighbor of our anode point, then there will be certain midpoint. There you can find some quantities like Jn and Jp. Using these two values, you can calculate the anode current. Of course, here and there you have a cathode point and the nearest neighbor to the cathode, and in between we have also an edge. For this edge, you can find also Jn and Jp. Then sum them all and multiply the area of your p-n junction. So not shown here explicitly, but assumed in our mind like this way, vertical to our x-axis. There is area A, then multiply this area, that will give you the current. So they are current densities, so they have the unit like ampere per square centimeter or square meter. So when you multiply the area, this area is gone, so we will have just a pure terminal current. Okay, and if you remember correctly, we need to be very careful about the sign. So which sign? Since terminal current is always given as positive when they are incoming and when they are incoming, so the meaning of incoming can be dependent on the contact. For example, when you consider this A contact, anode contact, actually this direction is the incoming direction. So when we have J and JP, their direction is always heading to positive x direction, so you must have negative sign. However, in the case of our cathode contact, actually incoming direction is aligned with positive x direction. So you can just multiply the positive number to Jn and Jp. So don't be confused with these signs. So when you apply positive anode voltage if you calculate it correctly, then your anode current should be positive, and at the same time your cathode current should be negative. Of course, the sum of your anode current and cathode current should vanish due to current conservation. But maybe you remember that in the previous lecture, I recommend you not try to apply this current conservation. Instead of that, first directly calculate your anode current and cathode current directly and use this current conservation to check the accuracy of your simulation result. If your result is perfect, then you will have the perfect equality between the sum of your current and numerical value 0. However, since we are not perfect in its numeric, so we are having the finite precision, so it is not guaranteed that we have exactly 0 value for this calculation. So don't be too much frustrated about non-zero value. But anyway, you can calculate this for the IV characteristics. Then let's go to the reverse one. So when you apply anode voltage, however, now let's assume that your anode voltage is now negative. Then what will happen? From the textbook, you may understand if we have IV characteristics, then if this is PN junction, wow, then you have learned that okay, this is quite much 0 and there will be certain exponential behavior. So we have already seen this part. This part is called as Ford operational mode, and now we are talking about this one. So the answer is somewhat unexpected like this. So when you have anode current, still this is linear scale, and here we have voltage, and this is my best result I can calculate from this double precision numbers. So are you with me? I mean that in textbook, so textbook says that okay, this is exact 0. Sorry, I will change it, my color, pencil color to other one to highlight it. So this is the exactly 0 current, and if we are in the reverse mode, so we will have, of course here we have 0 values, because when you apply 0 voltage, you are forced to have 0 current. This point is fixed, and you may think that maybe this is the graphs you can expect from the textbook. Here you have sharp increase to certain value. After that, this value is kept as just a constant. This is the reverse dark current. So maybe you have heard about it. So, however, what is the reality? So the reality is, even though we have performed the numerical simulation, the value of our current is so small, so orders of ampere per square micrometer. So now it is beyond the range of our numerical accuracy. Okay, so since this is too small current, so within our double precision calculation, it is difficult to get the correct answer. So then maybe you can think that, oh, since the current is completely long, our solution is just garbage. So inside it, maybe the quantities seems to be quite much unphysical, but it's not. When you just open and observe the point or the solution, it looks perfectly good. The only point is, our current is given by just a sum of drift term and diffusion term. And in this special case like reverse IV characteristics, then you can understand there is huge amount of drift term and huge amount of diffusion term, and they are perfectly matched to each other. So they are cancelling to the other. So now the remaining small thing, small result is that is reverse leakage current. So since this value is quite high and this value is quite high, so you know that's the problem. For example, it's like this. Here we have 10 to the 16, another number minus 10 to the 16. Then what will be the sum of these two numbers? So in double precision, what we can say is, since it's precision is more or less 14 digits, so if you have 10 or 1 or 0 0.1, that doesn't matter because it cannot provide us the accuracy down to 1 or 0 0.1, and also it cannot provide us precision down to 1 or 0 0.1. So the result shown here, orders of 1 or 0 0.1, doesn't make any sense in the numerical simulation. Okay, so since once again current, our current density is given as drift and diffusion. In the case of this reverse bias condition, both of them are quite high, quite strong, and they are cancelling each other. That's the reason why we cannot get meaningful value for this current conduction. So it reveals that the importance of precision. So what usually you do or I do is just double precision calculation. So when you just increase the precision of your numbers instead of your double precision number, you can use more accurate description about your floating numbers. Then immediately you get much better result. So when you use the commercial ticket tools provided by ticket vendors, they provide some capability to select the accuracy of your number description. So of course, when you increase the number accuracy or the accuracy of your number description, then you get much better result, especially when current is quite low. But point is, now it takes quite long. So increasing the precision, it takes longer time. So that is the problem, because every calculation should be done with much better accuracy or much higher precision. So the internal calculation takes a longer time. So that is the problem. Anyway, it means that now we can calculate reverse and forward IV characteristics. Okay.
지금 디펙트랑 디퓨전 둘다 큰 상황을 가정했을 때 다크커런트가 작게 나온다는 건 저게 그렇게 크지 않은 상황에서는 다크커런트가 커질 수 있는 건가? 뭐 개념이 잘 어렵지.
So now think about this one. So for example, so let me just quickly consider this one. Here we have a P-N junction. So let's say that this is a P and N. And in this classroom, everybody understand there occurs certain range of space charge. So in this part, actually, this part should contain a lot of holes and um, acceptors. However, holes are all depleted, so we just have accept ions. And in the case of this n-type region, actually we must have a lot of electrons and a lot of positively charged donors, but due to the depletion, we don't have any of electrons here. So now, from the viewpoint of our electrons, what will happen? Here, we have a lot of electrons, many electrons. And here, how many electrons are there? Almost no electron. So, from the viewpoint of our electrons, wow, this part, the p-type region, is just unexplored land, so there will be strong tendency to diffuse over this p-type region. So this large amount of flux is originated from the diffusion flux. However, since this part we have net positive charge, and since here we have net negative charge, so the electric field inside this PN junction is heading also in this way. This is not flux, but this is the direction of our electric field. Electric field comes from positive charge and NZ negative charge. So this is the direction. So from the viewpoint of our electron, then what is the direction of its motion when electric field is applied from right hand side and left hand side? Of course, there will be also strong tendency to the forcing our electron or pushing our electron to right hand side. So this is called drift. So in between, in this PN junction or depletion layer here especially, there is quite a high diffusion current and also quite a high drift component, and they are balanced perfectly. So that's the reason why we have almost, especially in the case of reverse bias condition, their magnitude are almost the same, and slight unbalance between them really makes this small current. So in the case of, let me just spend a small amount of time on this one. In the case of our reverse bias condition, let's say that this is a diffusion and this is drift, and in the case of our reverse bias condition, then actually we have a relatively larger drift term, and in the case of our positive or for the IV case, then we have a relatively larger diffusion flux. That's the reason why we have different behavior of our IV characteristics. Okay, so now let's come back to his question once again. He asked me that question. So okay, if this reverse current is originated from this large diffusion current and large drift current and large diffusion current, what happens if one of them is quite much negligible? And yes, so you can easily calculate or consider that situation quite easily. One case is, now here you have once again cathode, and here you have once again anode, and say that instead of a p-n junction you just have simple n-type material homogeneously everywhere. The electron density is just constant. Then what will happen to this case? In this case, you don't have any kind of meaningful diffusion effect. Okay, so now in this case, when you apply positive voltage or negative voltage to your anode contact, then only the diffusion will determine the current, and this drift term can be calculated quite easily. So yes, now you don't have such kind of difficulties when you calculate this just n-type bar or homogeneous n-type bar. So yes, therefore if you wanted to reduce this difficulty, what you can do is just to reduce the doping density to both sides. If doping density is reduced, then what will happen? Then you will have a much degraded electric field. So drift term is reduced. Also diffusion term is reduced because, for example, you have short range, and here you have 10 to the 20 and 10 to the 20 per cubic centimeter and per cubic centimeter. That was the situation. But instead of that, you have now 10 to the 18 per cubic centimeter and 10 to the 18 per cubic centimeter. Then what will happen? You have 100 times smaller density in your p-n junction. So now you will have a much smaller values for your diffusion current. Obviously also drift current will be reduced. So now it becomes much easier to match this balance between drift and diffusion. So your numerical problem can become much easier to be solved. So simply speaking, if you have a high internal electric field inside your device, then it becomes to get the leakage current accurately. So that is a common tendency you can observe. Okay, so are you okay with me? Okay, so now that was just the remaining lecture contents in our previous lecture 17. Then now let's go to the next topic. Up to now, we have successfully implemented the p-n junction simulator. Now you can introduce any values of dopant density. For example, for n-type you can try 10 to the 20, and for p-type you can try 10 to the 17, 18, anything. Also, you can just swap the dominance between n-type and p-type. For example, you can make, instead of n plus p junction, we have n plus p junction. You can also consider p plus n junction. So where can you find it? Actually, in your p MOSFET transistors, you can find it quite frequently. So in the case of n plus p junction, that is frequently observed in this case. Here we have transistors, and its source and drain is implemented with n plus region, and its body or substrate have the polarity like a p-type. So of course doping density is much higher than this substrate. So when we say that n plus p junction, then actually we are talking about this one-dimensional junction. So the reason why we are now working with this PN junction is to study the behavior of this junction. Then how about our P MOSFET? P MOSFET has the inverted polarity, and now it has its source and drain, which is implemented or realized with P plus regions, and it has relatively lowly clocked n-type region. So once again you can find this kind of one-dimensional junction. Okay, now but anyway, from your drift diffusion simulator, now you can consider any kind of arbitrary junctions with your device simulator. Seems to be quite perfect. However, the main topic of today's lecture is to reveal or disclose the failure of our previous implementation. Although we get the solution like this good and like this quite good, however, this kind of implementation is not actually used. So because it's a own difficulty. So let me just show it to you. But before starting this discussion, so let me just come back once again. So what we have to do, discretize in this 1D approximation. It is given by this way. Yes, we have it. And the point is, how can we treat the values of electron density and gradient of electrostatic potential and gradient of electron density? So in our naive implementation studied up to now, we made such kind of approximation. Yes, we just take the linear approximation and also another linear approximation and also another linear approximation. It means that inside this x sub I and x sub I plus 1, we have the linearity of our quantities like electrostatic potential and electron density. Both quantities are assumed to be linear inside this short or small edge. Okay, that was our naive implementation. Now let's go to this result. Seems to be quite strange and striking. So here we are now looking at the electron density at equilibrium. No other bias voltage, additional bias voltage is applied. So our anode voltage equal to 0, and of course our cathode voltage is also equal to 0. Drift diffusion result at 0 bias condition. And please have a look at it. So here we have 10 to the 17 per cubic centimeter as a doping density, and the overall structure have the overall length like 400 nanometer. So half of it was assigned to our n-type region, and the remaining half of them was assigned to the p-type region. That is the situation. And when you have a look at this leftmost graph, we have introduced 1 nanometer spacing for our system. since the overall length is 400 nanometer, so it means that we have 401 mesh points. Okay, then inside your system, how many unknown variables are available? Then the answer will be 401 times number 3. So are you with me? This number 3 comes from electrostatic potential, electron density, and hole density. So you have almost 1200 unknown variables. Well, anyway, when you have this kind of relatively fine grid having just 1 nanometer spacing, it seems to be okay because it starts from its doping density 10 to the 17, and here we have the metallurgical junction, the meeting point between our n-type region and p-type region. After that, our electron density goes down rapidly and eventually go to the level like this. Level of what? Level quite close, 10 to the 3 per cubic centimeter. What is this 10 to the 3 per cubic centimeter? This is the minority electron concentration, because here we have also assumed that another density was known, accepted density equal to 10 to the 17 per cubic centimeter. So hole density will be 10 to the 17 and electron density will be close to 10 to the 3. Are you with me? So product between your hole density and electron density at equilibrium should be the square of your intrinsic carrier density. So in this case it is about 10 to the 20. So I made a simple calculation. So although not very much visible, please have a look at here. Here we have actually two graphs. One graph is red one, and another one is blue one. Red one is actually not from your DD simulation, but it is obtained from your nonlinear Poisson equation. And blue one is corresponding to your DD simulation. So if everything is perfect, then what we expect is the red curve and the blue curve agree perfectly. And how about your opinion? So can you recognize any difference in this blue curve and red curve? Then the answer is okay. In general it looks okay, but when we have a look at this point, although quite small, but we can find a little difference between this blue curve and red curve. Then now let's go to another case. For example, here we have relatively coarse grain. So this is the spacing between two neighboring nodes, roughly 3 times more coarser than our fine grain. So in this case we have 129 mesh points. So when you have a look at this number, we are quite happy. Oh, previously we have used 401 mesh point and it introduced almost 1200 unknown variables, and now it is just contributing only about 400 unknown variables. Wow, it's good in terms of numerical efficiency. But please have a look at this red curve and blue curve. Red curve is identical when we make a comparison between this 1 nanometer spacing case and 3 point something nanometer spacing case, they look quite similar because they are coming from nonlinear quantification. But how about your opinion about your blue curve? Do you think that it is acceptable or not? Now you can see there really occurs meaningful and visible differences between your nonlinear Poisson equation and your drift diffusion model. Then maybe you may have two reactions. One reaction, okay, maybe it's not that much important. Because here we have quite small values like 10 to the 3 or 10 to the 5. Who cares about minority? I will not consider this one will be serious one. But no, it is really important. And second one is, well, since our drift diffusion simulator is more general and nonlinear Poisson equation solver is just concentrated or valid only for nonlinear Poisson equation solver equilibrium case. So the solution of our drift diffusion equation is the correct one, and this one seems to be a wrong solution. The answer is no. In this case, nonlinear Poisson equation should give us the correct solution, and it is now giving us the correct solution. So simply speaking, it's so simple. Our drift diffusion simulator, when it has applied to a coarser grid, then it doesn't work properly. Maybe once again you feel this difference is not that much, but if you say so, then I wanted to move to 10 nanometer case. Now spacing is just 10 nanometer and you have just 41 mesh point, and your unknown variable is just 120, actually 123. But anyway, in this case, still you have nonlinear Poisson equation looks perfect, but your drift diffusion result seems to be quite awful. Please have a look at this sudden drop here, and sudden drop here, and here we have no points here and only having the boundary value. What happens? What happens in this graph is in this point you have negative electron density, and here you have a midpoint, and here you have a midpoint, and here you have a midpoint. For these points also you have negative electron density. So when you just let it go, then when you apply your drift diffusion model to coarser and coarser mesh, then eventually your physical solution will predict negative electron density. So can you interpret this negative electron density with any reasonable way? So please don't be confused. For example, if you have minus 10 to the 17 per cubic centimeter, can you interpret it as, okay, it is actually corresponding to 10 to the 17 per cubic centimeter positive value for your whole density. It's not. They are not involved, not in this way. So, just simply speaking, your negative electron density just represent the failure of your simulation. Your electron density and hole density should be a positive number. So negative number occurs, it is an indicator for your failure. Okay. So now let's think about this case. Why do we have this kind of failure? What is the main cause? It is quite obvious. When you increase the step size, the spacing between your 2 points, then now you introduce something into your drift diffusion simulator, and your drift diffusion simulator cannot respond properly. That is quite much in contrast to our nonlinear Poisson equation. In our nonlinear Poisson equation, this lead curve, and lead curve, it reacts correctly even when we have a quite coarse grid. So please note that this graph, this red color, is not generated from this 1 nanometer spacing. It is calculated its own mesh, which has 10 nanometer spacing. So why our drift diffusion model fails and why our nonlinear Poisson equation still survive and gives a reasonably good result? That is my question. So of course you don't have to answer it right now, but let's have a look at more discussion. So yes, it is summarized here. Negative electron density. Simply it is nonsense. No other physical interpretation about negative electron density is available. So the negative electron density sorry about that. This is an indicator of failure of our discretization scheme with a coarse grid. So previously we had sudden jump from 129 and 41, and let's have a look at in between what happened. If we have 81 points and 51, it now becomes that 81 we just start to have negative quantities only here, and when we have less points, then its failure path becomes wide. So simply speaking, yes, the number of points or the spacing is the key point to determine whether our simulation fails or not. Okay, so do you have any question on these graphs? So if you have any question, then please let me know. Then please feel free. When you have any question, then you may interrupt me. So up to now, I have discussed about delta x dependence. It was obvious that if you have small delta x, then it's good. If you have coarse grid, then that was bad. That was the lesson from our previous slide. Then how about the doping? So up to now, we have used 10 to the 17 and 10 to the 17 for our n-type reason and p-type reason. Then now instead of that, now let's increase it a little bit. Instead of 2 times 10 to the 7, 10 to the 17, 10 to the 17, now we have 2 times 10 to the 17, 2 times 10 to the 17, or 4 times 4 times. Then when we have 10 to the 17 and 10 to the 17, yes, in this case, DD shows some differences between nonlinear Poisson result. However, it does not show negative electron density. But when we increase the doping density slightly twice, then what happens? Although still we don't have any negative density, but what you can see is, okay, the amount of deviation becomes larger. So the doping density has some impact on the quality of our solution. Eventually, when you go to even higher doping density, then now we can observe certain negative electron density occurs. So simply speaking, if doping is high, then that is a bad situation for our simulator, and if doping is relatively low, then that is good situation for our drift diffusion simulator. So let me just consider these two cases. What is the fundamental candidate for fundamentalism of these two delta x and doping. So doping can be just represented as electrostatic potential, because you know what is the relation between doping and electrostatic potential. It is given by just Vt thermal voltage and rho doping density divided by intrinsic carrier density. That is corresponding to your equilibrium potential. So absolute value of doping and plus minus sign due to its polarity. But anyway, doping is quite much related with the equilibrium potential. So simply speaking, when we have small when we have larger space, it is bad, and when we have large doping, it is bad. All of them can be attributed to a common factor of electrostatic potential. So now let's go. I will just keep this discussion later. However, before talking about more thing about in terms of analysis, let me just show you the result. Up to now, we just observe the failure of even at equilibrium. Even at equilibrium, our solution shows some differences from the correct solution obtained from nonlinear Poisson equation. How about IV characteristics? So here, this x-axis is not voltage. Please note that this is number of intervals. So number of intervals means that we now increase more and more points. So now you can expect that if we go to this direction, then that is the direction to increase our simulation accuracy. This becomes accurate and this becomes inaccurate case. And also this one is accurate case and this one becomes inaccurate case. Then please have a look at the difference. Although here we have certain values, however, when we introduce coarse and coarse grid, then eventually we almost lost all current. Please have a look at once again. In this case, here we have a certain value, accurate value. However, when you decrease the number of points and introducing coarser and coarser grid, then we will have some differences here. So between this 800 and 100, we get quite much fast simulation result, and at the same time we will get degraded solution. So of course here we have 2.88 and here we have 2.74, and the difference is just in terms of this scale. In terms of this scale we have just 0.114, and it is about just 5% error. Here and there we have a 5% error when introduce small significant reduction of points. But please have a look at this case. In this case, when we introduce 8 times a smaller number of points, then what happens? Previously we had 3.5 or slightly higher, and it is now almost close to 0. We completely lose the current. I mean that. So 100% error is involved in this case. So what is the difference between this left figure and right figure? These two figures obtained from different forward bias. So when we have sufficiently high forward bias, then error is not that high. However, if we go to the case which is close to equilibrium, then the error becomes higher. Okay, so yes. So are you with me, or all of our students? So this is important to realize the weakness of our current implementation. So what is the current implementation? The current implementation simply means that we have introduced all linear approximation to our physical quantities, electron density and electrostatic potential. We have assumed their linearity. So over the segment, then in this case, I told you that maybe the problem is all related with potential. So let me just check whether that is true or not. So I have plot some quantities at equilibrium. For example, now you may have certain point. Here you have phi I minus 2, phi I minus 1, phi I, phi I plus 1, phi I plus 2, blah blah blah. Then what I did in this slide is simply takes the difference between these two numbers and takes the difference between these two numbers and another two numbers. That is plotted here. And here we have spacing over 1 nanometer, 4 nanometer, and 5 nanometer. What was your expectation, your observation? Okay, in this case, it was good. The simulation quality was good. 4 nanometer, this is corresponding to 81 point. Then let's come back to our 81 case. Yes, this is 81 case. This is 5 nanometer. We already have negative density. So 5 nanometer case, where do we have a 5 nanometer case? Yes, here we already have negative electron density. Then how about 4 nanometer? That is corresponding to 100 point. Then do we have 100 point in this slide? Unfortunately, we don't have it, but now you may understand. Okay, although this is not as bad as 5 nanometer case, also that will be quite bad. So then the reason why I'm drawing this graph is quite simple, in order to check the maximum value and the maximum value and also the maximum value. What was the maximum value? Maximum value of difference, potential difference between two neighboring nodes. So in this good case, its value is approximately about slightly larger than 10 millivolt. Maybe this is about 12 millivolt. And this bad case, it is about more than 40, so it's like 45 millivolt. And this in this obvious failure case, 5 nanometer case, its value is somewhat larger than 50 millivolt. It seems to be about 55 millivolt. So so let me just come back. So let me just write this one. Read this one. Maximum potential difference of about 50 millivolt shown here seems to be a threshold for the negative density. When its maximum peak difference is larger than 50 millivolt roughly, then we have negative density. And when it is below below 50 millivolt, it becomes quite bad, but still we are free from negative electron density. Then my question is, why this number 50 millivolt occurs? Is this a special number? 50. What is your special number in this course? Maybe you know that 2585 millivolt, that is your special number. This number is corresponding to your summer voltage at 300 Kelvin currently considered in this course. But this is not 50. And another special number you may have is also 60 millivolt. So what was it? 60 millivolt was just our summer voltage multiplied by log 10. Since this is about 2.3, it gives us 60 millivolt. However, this is 50. So how can you relate this number with your VT? Do you have any idea? This 50 millivolt and VT. What is the relation between this one and that one? This is about 25 millivolt. Then simply you may say, although I don't have any reason for that, but maybe this 50 millivolt seems to be just twice of summer voltage. But why? Why we have twice summer voltage for the threshold of occurring negative density, electron density? Seems to be quite strange. So it seems that there is no reason why we must have this factor number 2. So number 2 seems to be redundant. Why do we have this kind of thing? Okay. Then now let's go to this one. Since this is too important, I will not start the discussion today because we must spend some time, sufficient time to discuss about this scheme called Schappeter-Gummel scheme. It is the name of two authors, Schappeter and Gummel. And yes, I think that as I announced before, next Monday I will just give you the recorded lecture, my comment on your term project, and Schappeter-Gummel scheme will be discussed later. However, before wrapping up today's lecture, I just wanted to stress the importance of Schappeter-Gummel scheme. Okay, so Schappeter-Gummel scheme, that scheme is the fundamentally important discretization scheme of TCAD simulation. So we are now approaching to the highlight of this entire semester. So learning this Schappeter-Gummel scheme and implementing it into your own code is the single most important task you have to do in this semester. So here we have certain presentation. So this is a special conference devoted to the TCAD simulation, the computational microelectronics, and previously there was a plenary talk by Professor Mark Lundstrom. He is a Purdue professor, and he's a big guy in this field, and his presentation title was Drift Diffusion and Computational Electronics Still Going Strong After 40 Years. So why 40 years? So starting from this one, please calculate 40 years ago. It was 1975. What is the reason for 40 years? This is related with the occurrence of Schappeter-Gummel scheme. When before Schappeter-Gummel scheme comes into the field, there was no way for us to robustically simulate this drift diffusion model. Only after Schappeter-Gummel scheme comes in, after that everything has changed. quite a lot. So simply speaking, previously your solution was only like this or like that. And by introducing the Shapiro scheme, even with this bad condition, now you can get good solution. The effect of Shapiro scheme is quite obvious. I mean that even when you have this quite coarse grid, although your naive implementation clearly fails, but your Shapiro scheme implementation will give you the exactly same solution like this red colored one. So that is quite much robust, and that will give you some advantages when you apply it to the realistic problem. Okay, I think that although my original plan was cover all of lecture material, but today was just devoted to motivate you for finding out a new scheme. So simply speaking, our previous naive implementation, it works. I don't say that it is completely a failure. It works only when you spend quite high computational burden with very small delta x value. Then you can get the solution. However, in reality, your delta x cannot be increased infinitely, so you must stop somewhere, and for somewhere usually your naive implementation does not perform quite well. So that's the reason why in the next Wednesday we will talk about the Shapiro scheme. So are you with me? Okay, then I will wrap up today's lecture, and let's meet again next Wednesday. I will upload my recorded video before our Monday session starts. Thank you.
그래서 이렇게 그 게임 중심에